Hi everyone, my name is Varun, and today I'll be presenting Lab 4, which was dealing with circuits and capacitors. So more specifically, our goal was to analyze DC and RC circuits using some circuit properties, such as the loop rule and the node rule, along with some basic tools such as the voltmeter and the ammeter. Some key takeaways from this lab were the conservation of energy, which was demonstrated through the DC circuit, as well as the steady-state nature of current. And we also explored the time-dependent nature of the charging and discharging of capacitors via an RC circuit. To demonstrate the steady-state nature of I, we created a DC circuit shown here with two 1.5 volt batteries and two resistors in series right here. And then there was an ammeter placed quote-unquote before and after the resistors to see the current that was passing through. Theoretically, the amount of current passing through should be the same because the current does not depend on time and it stays the same. So the total battery electromotive force was 3 volts, and the equivalent resistance is simply the sum of these two resistors since they are in series, 147 ohms, and our prediction was that both ammeters would read 0.02 amps. And that was correct. Both ammeters did read 0.02 amps. The next thing that was done was exploring the open circuit and checking what the voltmeter and the ammeter read. The voltmeter read 3 volts and the ammeter read 0 amps. This is because there is still a potential difference that is primarily supplied by the battery. However, because the circuit is open, there cannot be any current flowing for the ammeter to measure. Therefore, the ammeter had to read 0 amps. The next thing that was done was to demonstrate the conservation of energy using the idea of path independence and the round trip, and the fact that a round trip path potential change should be roughly 0. It should be exactly 0. So if we go clockwise, as shown in this picture at the bottom, then the sign of the battery's electric potential change is plus 3 volts, and then there are voltage drops that total 3 volts across both resistors, and then along all other parts of the circuit, all other elements of the circuit, there is theoretically no resistance, so there is no, and there therefore is no voltage drop across any of those circuit elements. The next thing that was done, again with the DC circuit, was to analyze what happens when we place a wire with no resistor in parallel with the 100 ohm resistor. The end result was that the current had tripled. But why is that? Using the node rule and the resistors in parallel formula, we can figure out exactly why that happened. So using this formula here, where 1 over the equivalent resistance equals 1 over R1 plus 1 over R2, we found that the equivalent resistance was actually 0. So this meant that the 100 ohm resistor essentially did not exist, and then the total equivalent resistance across the entire circuit was now just 47 ohms, roughly 1/3 of the previous, and the electromotive force stayed the same, and therefore the current had to triple. Some more calculations were done using the voltage drops calculated earlier with the electric potential graph, and the values shown here are roughly almost exactly what the theoretical values are, giving credence to the idea that this experiment was completed properly. The next thing that was done was looking at the RC circuit, which has time-dependent behavior. When the battery was first connected, the amount of current decreased significantly and then leveled out around 0. When the battery was removed and the capacitor began to discharge, the current began to decrease as well. The time taken to charge the capacitors was roughly linear. With a 10 ohm resistor, it took about 20 seconds to charge the capacitor and about 40 seconds for a 20 ohm resistor. The next thing is this equation at the bottom shows how the change in voltage and the relationship between electric potential, voltage, and time. And this -1 over RC value is the slope of the linearized version of this, which was done again just to generate a good model that is easy to analyze. So the This negative 1 over RC was negative 0.1666, as shown here. And this matches exactly with the theoretical prediction shown at the bottom right. Some final thoughts are that a real-life ammeter would read a lower current than the true current because an ammeter would have some resistance and add to the equivalent resistance of the circuit, and then resistance and current have an inverse relationship. Finally, without a resistor, a capacitor would be theoretically charged the instant the circuit is closed. However, because all circuit elements, even wires, have a little bit of resistance, charging would take a little bit of time, though not much. Thanks for listening.